Hey, everyone. I hope this is working. Let's see, this is Saturday evening, the 2nd of April. And we're having the class that I missed because I had to go to the hospital. Okay, this first page on our notes is just for your reference, and everyone will have a copy of this for the exam, for any quizzes. You'll always have a copy of these transformation codes, and also you'll have the order of operations. So let's look at something. We want to graph g of x. G of x equals -1/2 x plus 1 squared plus 2. So I can see that the parent function is x squared, y equals x squared. And that's something that you would fill in if it were a test. Even if it's a test, I'm going to list the points I want you to trace. So let's see, we want to first look to see how are we shifting horizontally, and where is the horizontal shift described? Do you see? Excellent. Yes, inside the parentheses. Horizontal things always happen inside the parentheses, and horizontal things are always opposite. So it says add 1, I'm going to subtract 1. So I want to shift horizontally 1 unit left. The rule is subtract 1 from x. So x is -2 here. It'll be -1. Y will stay the same. X is -1, but I just added. So it'll be -3, 4, -2, 1. 0 minus 1 is -1. Y stays the same. 1 minus 1 is 0. And 2 minus 1 is 1. Now we've got something going on vertically, stretching or shrinking. And that's why this blank is here. Is it a stretch or is it a shrink? I can tell that it's going to be a shrink because that number in front of the function is less than 1. It's between 0 and 1. Here we go. This isn't really green, but this will work. So I want to shrink vertically by a factor of 2. That means I'm going to divide y by 2. Alternately, I could say I'm multiplying y by 1/2. Whatever is easier is what we'll do. Well, here x is going to stay the same. So -3, -2, -1, 0, 1. And the y is going to be divided by 2. So let's see, 4 divided by 2 is 2. 1 divided by 2 is 1/2. 0 divided by 2 stays 0. 1 divided by 2 is 1/2. And 4 divided by 2 is 2. Well, that wasn't so bad. Now we're going to reflect. And the negative is outside the function. So we're going to reflect vertically. With respect to the x-axis. And the rule is that we change the sign of y. If the negative had been on the inside, we would have changed the sign of x. It would have been a horizontal reflection, and it would have been with respect to y. Okay, so let's see. Again, x is going to stay the same. So let's just copy those down. -3, -2, -1, 0, 1. And y is going to change sign. So 2 becomes -2. 1/2 becomes -1/2. 0 stays 0. 1/2 becomes -1/2. And 2 becomes -2. Finally, we're going to shift vertically. The vertical shift is always what is added or subtracted to the whole function. This time we're adding 2, so we're going to shift vertically 2 units. Let's get a color that matches. We're going to shift vertically 2 units up. The rule then is going to be add 2 to y. And I'm going to remember something because I've got some fractions here. I know that 1/2 plus, let's make it -1/2 since these are all negatives, plus 2, that's the same as -1/2 plus, let's see, 2/1 times 2/2. Oh, right, because if we multiply the 1 by 2, the denominators will match. So now we have -1/2 plus 4/2, and that's -1 plus 4, or 3/2. Good. Now when we fill in, we won't have to do all that math. So we're going to have -3 comma, let's see, -2 plus 2 is 0, -3 comma 0, -2 comma, here's a -1/2, so we're going to have -2 comma 3/2, -1 comma 0 plus 2 is 2, -1 comma 2, 0 comma -1/2, again, plus 2 is going to be 3/2, and then 1 comma -2, -2 plus 2 is 0. So let's look at these points. The original graph is the square. Y equals x squared. And it has points on it, 0, 0, 1, 1, 2, 4. The next point would be 3, 9. The next point going to the left would be -3, 9, because we're squaring every point. I do want to point out one thing. The name of this point where the graph starts going a different direction. It was going down, now it's going up. That's called the vertex. And we can see that the vertex of y equals x squared is just the point 0, 0. Okay, well, let's just sketch in these graphs. So let's see, I've got -3, 4, -2, 1, -1, 0, 0, 1, and 1, 4. This is the graph just of the horizontal shift. So this is the graph of y equals x plus 1 quantity squared. Groovy. Now let's do the vertical shrink. The points I have are -3, 2, -2, 1/2, -1, 0, 0, 1/2, and 1, 2. You can see that this graph is shallower than the previous graph. It just got wider, kind of. So this is the graph of y equals 1/2 times that x plus 1 quantity squared. So we're doing one little bit at a time. Well, now let's do the reflection, the vertical reflection. So we've got -3, -2, -2, -1/2, -1, 0, 0, -1/2, and 1, -2. That's not a beautiful graph, but that's okay. So this is y and x. This is the graph of y equals -1/2. So before we just had +1/2. We flipped it, so we've got a negative now, times x plus 1 quantity squared. And there's only one little thing left, and that's the vertical shift. Let's do that. Let's see, the points are -3, 0, -2, 3/2, -1, 2, 0, 3/2, what about 0, 3/2? I don't know what I'm doing. And then 1, 0. And this finally is the graph that we wanted. So I'm going to write its name. The others didn't get a name because they're not that special, but this one is. This is the graph of g of x is equal to everything we did before, -1/2 times x plus 1 quantity squared, all plus 2. Okay. If you have any questions about this, before you move on, pause the video and send me a text with a question. I'm available all until y'all have class. So just let me know that you have a question. We'll go over it, and then you can move on with the video. Okay, great. I've been thinking how we're going to do this group stuff. So I did on your own, but we've got a graph we want to figure out. So I want you to text me right now. Text me the parent function. I was waiting for some text. Isn't that silly? Okay, so I'm going to give you a few more minutes. Okay, now we've got another parabola, another quadratic function. So we're starting with the square. Let's get a black pen. Y equals x squared. Y and x. And we have 5 nice points. Y equals x squared, or the square function, is our parent function. And I can see that because I've got a 2 up above. I've got x raised to the 2 and really nothing else happening to the function, just shifting. All right. There are only 2 things happening with this graph. We're going to shift horizontally and we're going to shift vertically. So I want you to text me now. How many units are we going to shift horizontally? And are we going to go left or right? And then I want you to, in the same text, if you want, how many units are we going to shift vertically? And is it going to be up or down? So here, up or down. Here, left or right. Then I'll give y'all a few minutes. I can play the Jeopardy song. Dun, 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 dun. Okay, all right. I won't do that to you. Okay, awesome. So let's see. If we're subtracting inside the function, remember inside is always a horizontal thing and it's always backward. So Subtracting means add. So I'm going to go 2 units right. And the rule is going to be add 2 to x. For the vertical things are exactly what they look like. Adding 3 means I'm going to go up 3. So I'm going to go 3 units up. And the rule is add 3 to y. Okay, let's fill it in. So we're going to keep y the same, all right, 4, 1, 0, 1, 4, and we're going to add 2 to x. So -2 plus 2 is 0. -1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. Well, that was easy. This next step, we're going to leave x the same. So let's fill that in. 0, 1, 2, 3, 4. And we're going to add 3 to y. So let's see. 4 plus 3 is 7. 1 plus 3 is 4. I had a brain fart. 0 plus 3 is 3. 1 plus 3 is 4. And 4 plus 3 is 7. Now let's graph these things. So here's the parent function, this our friend the square. And let's graph just the horizontal shift. So I want 0, 1, 1, well, oh, 0, 4. Okay, I was wondering what. Okay, good. 0, 4, 1, 1, 2, 0, 3, 1, and 4, 4. Okay. And you can see that our graph really hasn't changed. It's just, we've just slid it over toward the right. The name of this graph is y equals x minus 2 quantity squared. All right, well, this one is kind of easy, not a whole lot to it. The next bit, we're going to graph 0, 7, 1, 4. So 0, 7, 1, 4, 2, 3, 3, 4, and 4, 7. And this actually has a name. This is g of x. So we have our original function. We slid it horizontally 2 units to the right, and then vertically 3 units up. The final graph, yay. Okay, this time let's look to see what happens. And in fact, let's look back at the other example too. The vertex, when we started, the vertex is the place where it changes direction. So vertex. The place where a parabola, that's the name of this shape, changes direction. Direction. Okay. So a vertex is the place where a parabola changes direction. It ceases going down and begins to go up, or the reverse. So we can see the vertex at the first shift has moved to 2, 0. And the final vertex is at 2, 3. Let's look at the graph, the name of the function. We subtracted 2, and that gave us 2. We added 3, and that gave us the 3. Let's see if it works with the other one. So here, our original vertex was at 0, 0. We shifted to the left 1 unit, and you can see the vertex is now at -1, 0. When we got wider, we did not change the vertex. That's very interesting. So here the vertex is still at -1, 0. Cool. This vertex is this point right here. What about when we reflected? How was the vertex affected when we reflected? Reflected. And it didn't move, did it? It's still at, so our vertex is still, yeah, that's right, at -1, 0. The only thing that changed our vertex so far was this horizontal shift. Well, what about the vertical shift? That does change our vertex. So instead of -1, 0, we're going to be up at -1, 2. And let's look at the function itself. I can write x plus 1 as x minus -1, because remember, everything inside it, the function is backward. So it's really -1, 2. And that pattern, because everything here is patterns, that pattern is something we're going to explore for the next, for the rest of the semester. So to see where the graph actually changes, all we need to do is look at the transformed function. Whatever is subtracted, so -1 is subtracted, that's the x coordinate of the vertex. 2 is added, that's the y coordinate of the vertex. Did that jive with what we had before? Let's see. 2 was subtracted, and that's the x coordinate of the vertex. 3 was added, and that's the y coordinate of the vertex. So it worked. Very cool. Well, now let's go back, because of course we're going to do many, many different things. And let's review factoring a quadratic that is 4x squared plus 4x minus 3 by grouping. So the first thing we want to do is find, well, let's first write down A. Let's see, A is 4, B is also 4, and C is -3. The two values we need are A times C and B. Let's see, A times C is -12, and B is 4. So I want you to think of any two numbers whose product is -12 and text those to me. Any two numbers whose product is -12. So I can think of, let's see, -6 and 2. -6 times 2 is -12, but -6 plus 2, let's see, -6 plus 2 is -4, and I want +4. So let's see, maybe if I do 6 and -2, 6 minus 2 is 4, and that's what we want. So we're going to rewrite 4x as 6x minus 2x, except we always put the -1 first if there's just one -1. So we're going to take this original quadratic, and write it as 4x squared minus 2x plus 6x minus 3. And we're going to group the first two terms and the last two terms. What's common between these first two terms? First, what's common between 4 and 2? Excellent. And what's common between x squared and x? Excellent. Okay, so let's see, 4 divided by 2, yeah, is 2. If I have two x's and I pull 1 out, I'm left with 1, minus 2x divided by 2x is 1, plus, because I put the positive number second, I have a plus sign in the middle. That really helps. Now, what is common between 6 and 3? Excellent. 6 divided by 3 is 2, and 3 divided by 3 is 1. At this step, we always look, let's see, at our two remaining binomials, binomial two terms, by two terms. And they do match. That's what we want. So we're going to factor that matching term out front. 2x minus 1. And now let's write down what's left. We have a 2x plus 3. And we're done. So it wasn't so bad. So we have that 4x squared plus 4x minus 3 is equal to 2x minus 1 times 2x plus 3. I want y'all to text me what A, B, and C are for example 4. So I've got 3x squared plus 2x minus 1. And I want to know what is A, what is B, and what is C. So A equals, B equals, and C equals. So text me those. I'll wait. Need a few more minutes? I'll give you 1 more minute. I'm hitting the bottom. Okay, so what is A? Excellent. And B? Marvelous. And C? Very good. So there are two things we care about. We want to know what A times C is, and we want to know what B is. The first is the product. The second is the sum. Well, let's see, A times C is -3 and B is 2. Think of any two numbers whose product is -3. Well, there's only one kind of way to get 3, just 3 and 1. So how do you get -3? We could have 1 times -3, or we could have -1 times 3. Is that right? Which one of these adds up to 2? Let's see. 1 minus 3 is -2. -1 plus 3 is +2. This is the one we want. Again, we're happy we only have one negative. We'll put that one first and the 3 second. So I'm going to rewrite my original as 3x squared. And instead of 2x, I'm going to write -1x plus 3x minus 1x plus 3x, and then minus 1. Okay, we're going to group the first two terms and the last two terms. This time, there's nothing common in the numbers. We do have a common x, though. So x times 3x minus 1 plus, and I'm going to put a 1 because it will help me later. 3x minus 1. Now, my remaining binomial, 2 terms, binomial, matches. So we're happy we've done it correctly. I'm going to pull that matching term forward, and I'm left with x plus 1. Do you see why it helps to write down the 1 if nothing is common between the two things? All right, that's it. Let's multiply that out just to see how it works. So we've got 3x minus 1 times x plus 1. And let's see if we really do get 3x squared plus 2x minus 1. I'm going to use FOIL, but you can use any way of multiplying that you like. So FOIL is just first, outside, inside, last. So the first terms are 3x times x. So that's 3x squared. And then outside is 3x times 1. Inside is negative 1 times x. And the last is negative 1 times positive 1, which is negative 1. We have 2 terms we can combine, these middle terms. So we get 3x squared. 3 minus 1 is 2. And then minus 1. And that's exactly what we wanted. So yay. Woo-hoo. All right, let's do another factoring by grouping. And this time it's not a quadratic, but factoring by grouping is actually one of the most useful kinds of factoring, more useful than factoring quadratics. It's as useful as the difference of 2 squares. So the difference of 2 squares and we'll remember that that's a squared minus b squared is a minus b times a plus b. This one is really important, and the factoring by grouping, really important. Those two you use forever. The longer you stay in math, the more you'll use them. Okay, well, just like always with grouping, I have to have 4 terms, and I'm going to group the first 2 and the last 2. Let's see what's common between these first 2. Well, there's nothing common between 5 and 4 besides 1. This first term has 3 x's. The second term has 2 x's. So 2 x's are common. If I have 3 and I pull 2, I'm left with 1. If I have 2 and I pull 2, I'm left with none. Okay. Now these last 2 terms are both negative. So what they have in common is negative 1. So let's see, negative 5x divided by negative 1 is positive 5x. Negative 4 divided by negative 1 is positive 4. Let's make sure that our remaining binomials match, and they do. Awesome. So we get 5x plus 4 times x squared minus 1. But look how happy, x squared minus 1. Perfect square minus perfect square. 1 is always perfect. So we get 5x plus 4. The square root of x squared is x. The square root of 1 is 1. I put a plus in one and a minus in the other. And we're done. Okay, the way we're going to work this next one, it's a factoring by grouping that I want y'all to do. So it means I'm going to do the work, but I want y'all to tell me what to do. So in these first 2 terms, how many x's are common? So I want you to text me how many x's are common. And also text me what is the largest common factor between 16 and 4. Okay, I'll give y'all some time to do that. Have some water. You need to, I'll give you another minute. Feel free to pause the video if you want to figure these things out. All right. So there are two common x's, so I can factor out an x squared, and I'm left with 4x minus 1. Then I've got negative 16 and positive 4. 4 is the largest common factor, but anytime there's a negative here in the middle, I have to factor out a negative. Whatever I factor out has to be negative. So I'm going to factor out a negative 4. 4 is the answer that I wanted. That's why I left the negative off here. So I have negative 16 divided by negative 4. 16 divided by 4, that's 4. Negative divided by negative is positive. Oh, okay, it's just 4. 4 divided by 4 is 1, but 4 divided by negative 4, oh, negative 1. Okay. And I'm happy because these two factors match. I'm going to factor out the common factor. So 4x minus 1, and check out what's left. X squared minus 4. So I want you to text me what the two terms, like before we had an x squared minus 1, and we factored that as x plus 1 times x minus 1. So how can you factor x squared minus 4? Go ahead and pause the video here if you need to text me. Okay, so here we go. I've got 4x minus 1. The square root of x squared is x. The square root of 4 is 2. And I put a plus in one and a minus in the other. And I usually switch it up because negative signs get a bad rap, and I like to give them a chance. And that's weird. Okay, awesome. Everything making sense? If anything anywhere along here doesn't make sense, please pause the video and text me, and I will absolutely help. Okay. We have a little bit more factoring to do today, but factoring is never over. It's one of the happiest parts of math, of algebras, factoring. It's like a puzzle. It's really fun, and we're just looking for patterns, 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 patterns. And in fact, here's case in point. We are going to factor this quadratic not by parts, not by grouping, but by patterns. So let's see. This first term and the last term, they're both perfect squares. Anytime you have a quadratic, quadratic is what we call, let me write the word down, quadratic. That's anytime we have an x squared term. Anytime you have a quadratic where the first term and the last term are perfect squares, check this little thing out. Try this. Let's take the square root of the first part. So the square root of 4x squared, let's see, square root of 4 is 2, square root of x squared is x. And let's take the square root of the last term. What is the square root of 25? Good. And let's take these two remaining terms and multiply them by 2. So let's take these two terms and multiply them and multiply by 2 as well. So we get 2 times 2x times 5. That's 4 times 5 is 20x. How does this compare with the middle? It matches. We don't care about the sign. We just care about the number. 20x, 20x. That means that 4x squared minus 20x plus 25 is a perfect square trinomial. Perfect square trinomial. Tri means 3, nomial means terms, so 3 terms. And let's write it in the form that we saw when we found products. This is 2x squared minus 2 times 2x times 5 plus 5 squared. And that's exactly what it looked like when we expanded a minus b squared, where a here is 2x. The minus is from the original thing. It's a negative, so we put a negative. And then b is 5. It's all kinds of fun. All right. I want you to text me for example 8. What is the square root of x squared? And what is the square root of 9? Okay. The square root of x squared is x. Good. Square root of 9 is 3. Let's take these and multiply them together and by 2. So we have 2 times x times 3. That's 6x. 6x, 6x. Yes, we have a perfect square trinomial. Perfect square trinomial, trinomial. And we can write it as x squared minus 2 times x times 3 plus 3 squared, which is exactly the pattern of x minus 3 squared. We're just always looking for patterns. Always, always, always looking for patterns. All right. Now we're going to look at some definitions. And even and odd are names that go with the kinds of symmetry we've looked at already. So if something is symmetric with respect to the y-axis, we say it is even. If something is symmetric with respect to the origin, remember that's like twice folding, we say that it is odd. And let's see why those names happen. First of all, an even function is any function where if you change all the x's to negatives, you haven't changed the function. A function is odd if when you change all the x's to negatives, you get exactly the negative of what you started with. So let's look at some examples. Here's g of x is x squared minus 1. We want to find g of negative x. So let's see, what in the world? So g of x is x squared minus 1. G of negative x. Well, the only thing I'm changing, the only x is this first term. I'm going to change it to negative x. But what is negative x squared? Yeah, exactly. It's the same as positive x squared. And so this g of negative x actually does equal g of x. That means that g is even. And what do you notice about the exponent? Is it also even? And even functions are symmetric with respect to the y-axis. And we know this graph really well. X squared is the parent function. We're shifting 1 unit down vertically. So here's y or g, we are calling it g of x is x squared minus 1. And you can see if we reflect with respect to the y-axis, it will match. So even and symmetry with respect to the y-axis are the same. Well, let's try something that's a little different. Actually, let's look at the third one and then go back to the example that we skipped. So we want to see, does f have symmetry with respect to the x-axis, the origin, or neither? And the way we do that algebraically, if we don't want to graph, is that we just plug in negative x everywhere there's an x. So to see whether f has any symmetry, we're going to plug negative x in for x. So I've got f of negative x. Everywhere there's an x, I'm going to change it to negative x, and I'm going to use parentheses. So negative x cubed minus negative x. Did I do that correctly? Excellent. So let's see. Negative x times negative x, just squaring it, we get positive x squared, times another negative x, we get negative x cubed. And the negative times a negative is positive. And now this definitely doesn't match our original. So let's factor out a negative and see if that will make it match. So if I factor out a negative, I'll get positive x cubed. And then positive x divided by negative 1 is negative x. Now, how does this compare with our original? Hey, it matches. So we have negative f of x. And that means that f is odd and that f is symmetric with respect to the origin. What do you notice about the exponent? Well, the first term is x cubed. What do you notice about the 3? Is it even or odd? Yeah. And if there's no exponent written, what is the exponent that's always there? Good. Is 1 even or odd? Exactly. So both of these terms have odd exponents. And we found out that the function itself is odd. It's not a coincidence. Okay. Well, this one, I guess I'm going to do it with y'all. So we are starting with h of x equals 1 over x. And we want to see what happens when we substitute in a negative x everywhere there's an x. So let's see. h of negative x is 1 over negative x. So everywhere there's an x, I'm going to put parentheses, negative x. But remember, with fractions, negative a over b is the same as negative a over b is the same as a over negative b. I can move that negative anywhere I want, and it's always the same. So this is the same as negative 1 over x, which is exactly negative h of x. So is h even or odd? Go ahead and text me with the answer. Is h even or odd? Okay, great. H is odd because h of negative x was negative h of x. It was exactly the opposite. When we plugged a negative x in, we got exactly the opposite of what we started with. Let's sketch it and see if it's odd. It should have symmetry with respect to the origin. So let's see. I kind of remember what h of x equals 1 over x is because it's one of our parent functions. So let's see, I've got the point 1, 1 and negative 1, negative 1. And then 1/2, 2, and 2, 1/2. Negative 1/2, negative 2, negative 1/2, and negative 1/2, negative 2. Let's do one more batch. We have 1/3, 3, and 3 1/3. And we'll have the same points in the negative. And let's go ahead and draw this in. Remember that these are half arrows because the graph will never touch either axis. No matter how far, no matter how large x gets, in other words, no matter how far in the positive infinity direction we go, 1 over a huge number is still not 0. It will never touch the x-axis. It will never be 0. And if we never get 0, we'll never get, oh, right. And so no matter how small the number is that we plug in, tinier and tinier and tinier numbers, the answer is going to get huge, but never, we can never hit 0. So we say that the x-axis and the y-axis are asymptotes. Asymptotes. It's a beautiful word. You pronounce every letter, well, except that E. Asymptotes. So an asymptote is just a line that the graph gets close to, but never touches. Now, do you see why this function is symmetric with respect to the origin? If we fold it along the y-axis, this part of the graph in the first quadrant will move here into the second quadrant. And if we fold again along the x-axis, then the two parts will match. So twice folding makes us match. That means we've got symmetry with respect to the origin. Okay. So even and odd, we're adding descriptors and an algebraic property to symmetry. Now we're going to look at something that I just want you to follow. These are vocabulary terms that we're going to use in the future, and I want you to know what they mean. So increasing, decreasing, and constant requires that we know what an open interval is and what a closed interval is. And it's actually pretty simple. An open interval doesn't include its endpoints. So in other words, if I have A and B on the x-axis, an open interval doesn't include A and doesn't include B. A closed interval does. A closed interval does include the endpoints. So we say that this interval A to B is closed and that this interval A to B is open. Increasing, decreasing, and constant are terms that we only describe to open intervals. So we don't ever include the endpoints. A function is increasing or going up if when x1 is less than x2, f of x1 is also less than f of x2. So let's look at the picture. Here's x1 and x2. Here's f of x1 and f of x2. If we go toward the right, so from left to right, the function increases as x increases. Let's look at the next image. Here's x1 and x2, f of x1, f of x2. As we go from right to left, x is increasing, but f of x is going down. So that's this description right here. A function is decreasing on an open interval I if whenever x1 is less than x2, f of x1 is actually larger than f of x2. So when x is getting bigger, y is getting smaller. A function is constant on any open interval if no matter what x you choose in the middle, you still get the same value. You always have the same f of x. Maxima and minima are terms, all of these terms are terms that you're going to use as long as you do math or science. So a maxima is any kind of maximum. So this is the singular, and this is plural. And the same with minima and minimum, singular, plural. So more than one minimum, more than one maximum. All right, we have two kinds of maximums. We have a relative max and we have a global or absolute max. And we almost always call maximums maxes and minimums mins. We have maxes and mins. Let's look at this image because it actually makes everything very simple. As I'm going from left to right, let's see, the endpoints are always a category. So here, this endpoint is low, so it'll be a min. I don't know yet if it's absolute, but it'll be a min. So we would say that's a relative min. And keeping going, here's another place where it goes down and back up. So another relative min. And I'm only looking for mins right now. Here's another relative min. Relative min. Because all three of these points are in their little area, they're the lowest value. The absolute min is the lowest of the three. Well, let's look at the maximums. I'm just going to trace from left to right again, but this time I'm only going to look for places where the function goes up and then back down. So here's a place. Here's a place. So they're both, if you see, they're both relative maxes. The second one is an absolute max as well, because it's the larger of the two. The extreme value theorem is a theorem that you use a lot. Unless you're majoring in math, you probably will never have to prove it. Everyone who majors in math will get to prove it. But even people who don't major in math definitely always use this extreme value theorem. Engineers, physicists, chemists, anyone who's working with any kind of math. A continuous function can, for us, because continuous continuity requires calculus to define, but we're going to say a function is continuous if you can draw it without lifting your pencil. So without lifting a pencil. So a function that is continuous and defined on a closed interval, so we are including endpoints, has an absolute maximum and an absolute minimum on that interval. So every continuous function on a closed interval has an absolute max and an absolute min on that closed interval. All of this is important for vocabulary, so that when we talk about, I'm not going to throw extreme value theorem at you, but I will talk about maximums and minimums. I will talk about open and closed intervals, and increasing and decreasing functions and constant functions. Oh, another important note, a maximum and or a minimum, those are numbers, not points. So intercepts are points, not numbers. Maximum and minimums are numbers, not points. So they're exactly the opposite of each other. Let's find the maxima and the minima for this really cool looking graph. So we always include the endpoints. Let's see. So this is definitely, I'm going to go ahead and try to identify the points. Let's see, this is 10, 9, 8, 7. 2, 4, 6. So this must be 5. I'm just going to label all of the endpoints really quickly. So the next one is 1, 2, -4, and -1, 2, 3. And then it goes up to 1, 2, -3, 0, 0, 0. That looks like 1, -1. And then 5, 7. This is 8, -2. and 12, 1. Okay, now that we have all of those points labeled, it'll be easier to talk about intervals where the graph is, excuse me, increasing, decreasing, constant, and then numbers that are absolute and relative maxes. So the function is increasing if it's going uphill, if we're reading from left to right. It looks like this little section between -4, -3, and -3, 0, it's increasing. The interval is always on the x-axis. So I'm going to say it's -4 to -3. This is the interval. Where the function is increasing. But wait, there's more. So from from 1, -1 up to 5, 7, the function is also increasing. That interval, let's see, it's always the x's, so 1 and 5, and we don't include the endpoints. So this is increasing. And then from 8, -2 to 12, 1, the function is increasing again. That interval is 8, 12. So I would say that the function is increasing. On this interval, -4, -3, union. Union 1, 5, union 8, 12. Let's see where it's decreasing. It's decreasing in this beginning bit. So -7 to -4, decreasing. It's decreasing between 0, 0 and 1, -1. So that's the interval 0 to 1. And it's decreasing from 5, 7 down to 8, -2. So decreasing on the open interval 5, 8. So let's put that all together. We have -7, -4, union. Union is read as or. Intersection is the other one. Intersection is read as and. Okay, so decreasing, we've got -7, -4. We also have 0, 1. And we had 5, 8. And we actually do have a place where it's constant. And it's constant between -3, 0 and 0, 0. So I only care about the x's, -3, 0, without the endpoints. To find the absolute max and the absolute min, we're going to first find all of the relative maxes and relative mins. So it looks like -7, -5. So I'm going to put 5. The y's are always the mins and maxes. X's are the increasing, decreasing, and constant. So let's see. Y equals 5 is a max. Looks like y equals 0 is a max, a relative max. Y equals 7 is a max. Those are the 3. And of the 3, which is largest? Good, good. So we would say that y equals 5, 0, and 7 are the relative maxes, and the absolute max is 7. What about the relative mins? I've got -3, the y, -1, -2, and of the 3, which is the larger or the smallest, yes, -3. Do you see how that goes? Loads of words to describe pretty simple ideas. Okay. I want y'all to tell me what to write down and I'll write it. So let's see how we're going to do that. Let's do the same thing we did on the other graph. Let's label all of the endpoints. This one is easier to read. That point is -1, -2. This point is 2, 1, then 3, 0, then 4, 1, 6, 1, and 8, 0. The function is increasing when we go from left to right, the function goes up. So as we're going from left to right, looks like this interval from -1 up to 2 is increasing. And it also looks like this section between 3, 0 and 4, 1, the function is increasing. So the x's are 3 and 4. And that's it for this function. Where is it decreasing? I didn't label that. So I want you to tell me, text me which intervals this function is decreasing. On which intervals is this function decreasing? So text me that. Go ahead and pause the video if you need to so that you can text me. All right. So yes, I can see that from the point 2, 1 to the point 3, 0, the function is decreasing. So the open interval from 2 to 3, and also between 6, 1 and 8, 0, the function is decreasing. So open interval 6, 8. The function is constant between 4 and 6. These intervals are always not including the endpoints. Okay, let's look at relative mins first, because we start with 1. We start with the low. So I've got a relative min of -2, a relative min of 0, and another relative min of 0, which I don't need to write twice. Which one is absolute? Yes, good. The relative maxes, I've got a point 2, so 2, 1, so the value 1, and that's it. There's just the 1. So the absolute max is is there really an absolute max on this graph? If we've got loads of places where the graph hits that maximum point, and it depends upon your teacher. I would say this does not have an absolute max, but it has a relative max. It doesn't have a single point that is larger than all the others. All right. One more like this. So we have a graph, and this time the graph also includes open and closed points. The point 1, 1 is closed because it's filled in. We include that point. Closed means include. The point 1, 3 is open We don't include that point. The point 2, 3 is closed. What about the point 2, 2? Is that open or closed? Go ahead and text me. Is 2, 2 open or closed? Is 2, 2 open or closed? Okay, that's right. It's open. We don't include that point because it's not filled in. All right. Well, we've labeled all of the endpoints except this one here at 0, 0. Where is the function increasing? Good. This little section between x equals 0 and x equals 1. And the section between x equals 2 and infinity. Where is it decreasing? Good. So just one interval, negative infinity, all the way down to 0. So this whole part of the graph. Where is it constant? I want you to text me the interval on which this function is constant. Okay. And yes, that's right. It's constant between x equals 1 and x equals 2. So 1, 2. Let's fill in the relative maxes. So let's see. This is a relative max. So we have the y1. This is a relative max. So we have the y value 3. And that's it. So we have a relative max here and here. No other relative maxes. If I go to the right, the function goes to infinity. If I go to the left, the function goes to infinity. Is there an absolute maximum for this function? Exactly right. The relative minimum, well, let's see, there's just, no, actually there are two. So we have the point at 0, 0. And we have this point at 2, 2. And which one is smaller? Good. And do you see that in this case, it's more obvious than some of the others that the point 0, 0 is the place where the graph has its absolute lowest value. So we do have an absolute minimum at y equals 0. Okay, go ahead and take a break. I'm going to pause the video, take a break, at least 10 minutes, and then come back. Oh no, I just now resumed the video, done all this stuff. Okay. Actually, I think I'm going to stop this video and make another one. So, because I've done a lot of stuff and I wasn't recording. So, respond to all of the